Hi everybody, I thought I would give you a quick update on Cerberus 2100 because there are some changes, some exciting news. What you see here on the board is fairly different from what you saw before in terms of size and less components. What happened is that I have been having discussions with a commercial party that may, no commitment, may want to manufacture and commercialize this in volume. And the idea is to save work as much as we can. So since I'm going to design a board to prototype and for myself anyway, I thought I might as well design it according to their preferred trade-offs using the components that they have in stock, doing it in such a way that perhaps they can just take the Gerber files and manufacture it without having to redesign anything, to port anything, without having to make an investment in manpower. So that's what we've been trying to do. And the key requirement is, of course, cost. They want the cost to be as low as possible, which is understandable and it's good for the community. It makes it more accessible for people. Look at what happened when Olimax commercialized Argon Light and made it available for 50 euros. Hundreds of people have Argon Lights now, and they just begun the rollout, and it's already hundreds of people. So it's good for the community. So I decided to go for design for manufacturing and design for cost, which I normally don't do. I'm a hobbyist. I just like to make things over-engineered and nice. But it helps the community. So you will notice that we lost 2 chips. There used to be 3 buffers. This is one of them in here. There used to be another one here in the middle. There used to be another one here down below. And those 2 are gone. They are replaced with single gate buffers where needed and not anything more. These single gate buffers, you see one here, U2 over here is a single gate buffer. There's another one here, U5 is a single gate buffer, some transistors around. So that's that will certainly be cheaper. There is only one expansion port instead of the 4 single row that I had before, made the board very large. The idea we have now is now we have an SMD expansion slot, which is much more, it's much cheaper to manufacture because you don't have to hand solder it. And 2 rows instead of only one, and we put only one slot. And the reason is, with an IDC flat cable, you can connect a flat cable here and connect it to another board with more expansion slots. In that other board, you can have a mini backplane with 4, 8 expansion slots. But many hobbyists only need one because they will be designing one card at a time and they want to test it with the system. So they only need one. Why should they pay the price for 4? And the ones that do want 4, I will personally make sure that there is something on GitHub. There is a design on GitHub that you can order, and you get an extra backplane that you can connect to this with an IDC cable, and then you can have 4 or even more expansion slots. So that allowed us to reduce the board quite a bit. You see a male IDC connector here. The footprint on the board is almost identical to a female connector, a female header that the commercial party I'm discussing with has abundantly in stock. So they'll probably commercialize it, if they do at all, they'll probably commercialize it with a female header instead of a male IDC connector. For me, it doesn't matter much. I tend to prefer male connectors because they last longer. But female connectors have other advantages, like reduces the chance of short circuits, accidental short circuits. I also removed the transient voltage suppression diodes that I had here connected to the expansion slot because this bus transceivers, you see BT1, B2, BT3, these are bus transceivers for the address and data bus. And then we have a buffer here for the control signals. They all have some level of ESD protection, and that on top of having either a female header or a shrouded IDC male connector reduces the chances of electrostatic discharge already anyway. The JTAG headers that you see, one here, and one here, they are now SMD. So just a pick and place machine puts it there. You don't need somebody to come with a hand solder and solder 30 solder joints by hand. So that should make it cheaper. There was an opportunity to take away 2 of them and daisy chain the JTAG signal. I didn't do it for 2 reasons. One, these connectors here, they cost like 35 cents in low volumes, less in high volumes. So they cost very little anyway compared to the cost of the chips. And to daisy chain, I would need 3 global nets that would do a lot of via hopping, and so electrically it's not ideal. And also for users, if you daisy chain your JTAG signal, you have to know how to configure your files when you're going to program the JTAG chips, because now you have only one connector for all chips, and you need to know how to send the correct configuration file to the correct chip. It's not difficult at all, but it adds one more little layer of complexity. So I thought I will keep the separate JTAG headers, so you know that if you're using this header, you're programming this CPLD skunk. If you're using this header, then you're programming Kavia, this other CPLD. Or if you're using this one, you're programming Spacer, which is the third CPLD. So there are 3 CPLDs. Kavia here. Kavia is responsible for scanning the video memory in order to generate the video signal. So it's constantly scanning the video memory. It's a relatively small CPLD. I'm using a large package with lots of pins, 100 pins, although I use only like less than 1/3 of that. And the reason is this version will become available sooner, in May this year, and in higher volumes than the smaller version, say a PLCC 44 version, which is, it will become available later and in lower volumes. So that's why I'm using the large package here. So Kavia, it's a CPLD, a complex programmable logic device. It's not akin to an FPGA at all. CPLD is much more akin to the gate arrays of the 80s. So this is not an anachronistic part. It's period authentic. This is a kind of educational retro computer meant for universities and hobbyists who want to learn how a computer is put together, a complete system. So a CPLD has this advantage that when you look at the design files of a CPLD, the design is specified explicitly down to the gate level. You can see exactly which flip-flops, where there are flip-flops, where there are AND gates, NOR gates, and how they are connected together. And the propagation delay is extremely predictable. And that's contrary to FPGAs, which you program with a high-level language like VHDL or Verilog. And then you have an automatic synthesis tool that translates that into a netlist. And usually the designer doesn't know what is on the netlist, doesn't care. The designer just specifies the functionality. The tools actually do the synthesis of the hardware. I think that's not very educational because it's kind of a black box. CPLDs are not. CPLDs, you look at the design files and you see the specification of gates. It translates one-to-one to a gate level schematics. So the design is very visible, very predictable. Even the propagation delays is very predictable. So Kavia scans the video memory. The results of that go to the character memory, because in each video memory location, there is the code for a character that should be displayed on that location. So that information goes to the character memory in here. And Skunk is the CPLD, also CPLD, and it's responsible for actually generating the video signal. It generates the 2 sync signals, the vertical sync and the horizontal sync. Needs a lot of flip-flops, a lot of counters in this. So here, this is a bigger CPLD inside. The internals have more logic than Kavia. So it generates the sync pulses and also takes the character information from the character memory and puts it in the video signal that comes out of this buffer in here, goes through a large resistor into the RGB lines. CERBERUS is a black and white machine because it's not focused on, colors and sounds and games. This is an educational machine. So I wanted to put in it everything that makes a complete system, but not anything more that would lead to extra complexity that takes more work from students to understand. I wanted to keep it as clean as possible. So that's Skunk. It generates the actual video signal, including the contents of the characters that are sent to the VGA. These are the 2 dual-ported memories. Video memory here, 2 kilobytes. Character memory here, also 2 kilobytes. Let's see if I can animate it. Yeah, 2 kilobytes of video memory, 2 kilobytes of character memory. Then we have the system memories in here. High memory, 32 kilobytes. and low memory, 32 kilobytes. So 64 in total, but only 60 are addressable because there are two times 2 kilobyte memories in here that takes 4 kilobytes of the address space. So one of these memories has 4 kilobytes that aren't addressable, although they're physically there. These are the actual system memories. Then we have the two CPUs, that the W65CO2, which was developed amongst others by Bill Mensch. I have a little homage to Bill in here. And this is the Z80, which was designed by Federico Fagin, who happens to be a friend of mine, back in 1974, the year I was born. And I have great admiration for Federico, not only because of his electronics engineering, his computer engineering, but also because of everything he has done in his life after that. When it comes to foundations of physics, neuroscience of consciousness, he's doing a lot of great work. So I pay homage to him here as well, and I put a little photo of him on the board. This Cerberus is a celebration of the early days of computer engineering. So it makes sense that we pay homage to the greats that started this whole thing. And then here in the middle, that's the maestro. That's the conductor of the orchestra. That's spacer. It's also a CPLD, a large one. And in this case, I'm using almost every pin. If we were to do with 74 logic what spacer does, we would be using well over 100 chips. So no, we put a big gate array in there, CPLD, to do all of that logic that provides a layer of abstraction. So the system is CPU agnostic. You can use a 6502 with it. You can use a Z8 with it. You can use a CPU that the user may plug here on the expansion slot. And you can even use a microcontroller, a modern RISC processor like this Atmega 328P. I call CAT for custom Atmega because the registry is changed in order to allow a strong 4-pin oscillator that you see in here to provide the clock signal, as opposed to a crystal with capacitors or the internal oscillator. So CAT via spacer, these two are the conductors of the system. They are the maestros. CAT has the firmware, and spacer provides this large logic that allows the system to be very, very flexible. Now, the usage of dual-ported memories allows for the video generation circuitry here on top to be completely asynchronous from the computer proper here on the bottom. So the computer proper uses a 16 megahertz oscillator. The video signal, because it's VGA, uses a 25.175 megahertz oscillator. So they are completely asynchronous. And that has an advantage. If students or hobbyists want to play with different logic here on the computer proper, they don't need to worry about maintaining sync with the video generation, because it's asynchronous anyway. So they can forget about the video generation part and just play here with the logic in spacer, which can be reprogrammed as many times as you want via the JTAG header. Well, not as many times as you want. I think just after a few thousand programming cycles, the next time you do it, it may not work very well, but you can reprogram it a lot. And playing with the firmware in CAT, which is written in C and stored in the embedded flash memory of CAT. Cerberus does not have an EEPROM. The firmware is in the embedded flash memory here of the Atmega microcontroller. So you can play around with changing Cerberus and turning it into a different computer by writing a new Arduino sketch for CAT and programming the logic in spacer differently. You can just play around with it and not worry about the video circuitry. On the other hand, if you want to fool around with the video circuitry here on top, these two CPLDs, there is a DAC in here, then you can do that without worrying about the computer proper, without worrying about changing the firmware. So that's one of the advantages. Now this stuff you see here, that's a 5 to 3.3 volt LDO, low dropout regulator. And this is basically a level shifter, and the idea is to allow for the use of micro SD cards, which operate at 3.3 volts. The header here is to program the bootloader in CAT, and this connector here is to allow you to connect an FTDI adapter to reprogram the contents of CAT's flash memory. In other words, to reprogram the firmware. What else is there to show? Yeah, these are the bus transceivers. This is what allows whatever you connect to the expansion to interface with the system buses in here and the control logic in here. There is a USB connector for the keyboard. It needs to be a PS2 keyboard. Just like for Argon Lite, we need to use a PS2 keyboard, but there are several vendors that sell USB keyboards that are PS2 compatible. So we put a USB connector there. That's a preference by the potential party that may volume manufacture and commercialize this. Power is USB-C, directly 5 volts. Unlike the original Cerberus, in which I used the 12 volt or 9 volt barrel connector and had local regulation, which is more robust. Here, to reduce costs, we just put a USB-C connector and allows you to just take any 5 volt USB charger that you have lying around. There are millions of them now. Any one of them would do. You just connect here and provide power to the whole thing. There's a large 470 microfarad cap for decoupling right next to it, because since we don't have onboard regulation, decoupling now becomes essential. In addition to this large electrolytic, I have 6 of these smaller ceramic capacitors here, which are 100 microfarads, and they are distributed across the board here. One of them is dedicated to decoupling for whatever the user connects to the expansion port. Here on the corner, we have the audio circuit, which is very simple. An audio signal comes from CAT, and then it's buffered by U3. There is a little header here. If you put a jumper on the header, you would disable, you tri-state this buffer here via an inverter. You tri-state the buffer and the buzzer will produce no sounds. So this is for people who find the buzzer sounds annoying. You can just disable it by putting a jumper here on this header. After that, you just have a very simple RC filter to soften a bit the sound, because it's a square wave. So by putting an RC filter, you sort of you soften the corners of the square wave and makes the sound a little bit less annoying. So that's it there. Here you see is just a large cap to decouple whatever the user connects to the expansion board. There is a fuse there in case the user connects something that has a short circuit, which will happen. Hobbyists will find a way to short circuit their design and connect it here. We don't want Cerberus to be blown because of a prototype card with a short circuit. So this fuse here will just protect Cerberus. And it doesn't blow like a normal glass fuse. This is a solid state fuse. What happens is that if you drain more current than you are allowed, the fuse opens. But the moment you stop draining that excess current, the fuse reconstitutes itself. So it doesn't get blown. It protects the circuit, but doesn't become useless. It just goes back to where it was. And there is an ESD protection device here, just to protect Cerberus from whatever ESD, electrostatic discharge you may put on the power pin. The other pins, because they go through the buffers and transceivers, they are ESD protected by the buffers and transceivers. These resistor banks here are through-hole because they facilitate the routing a lot. VCC is routed on top, so it gives me a sort of virtual extra layer for routing. That's why I'm using through-hole in here. And these are pull-ups for the system buses. System buses should always be pulled, either high or low. High is preferred for a number of reasons. You should never leave system buses unpulled, because if there is no chip driving the bus, it will float, and that can have all kinds of consequences that you don't want. So this is basically it. That should be the final looks of Cerberus 2100. I had a discussion with the commercial party. I got an email from them just today, and the last desire they had was to have SMD connectors here for JTAG, which now they are. As you can see, they are now SMD, no longer through-hole. So this is hopefully the final looks of the computer. Just to give you an idea of the dimensions, side to side, it's about 13.3 centimeters. Side to side, let's have a look. I actually may have forgotten. Fabrication, PCB information. Yeah, 14.3 centimeters times 11.1 centimeter. So this will fit comfortably in the palm of your hand, and you can even wrap your fingers around it. your hand will have 20 to 30 centimeters side to side. So this will fit comfortably in your hand like this, allowing you to wrap your fingers around. So it's pretty tiny, and hopefully it will be much cheaper. The CPLDs and the 2 dual ported memories are relatively expensive, but much cheaper than a big FPGA would. Here I would have to use a very large FPGA because I need the pins. And if you buy an FPGA with 100 pins, that will cost you. CPLD will cost a lot less, but it's more costly than, for instance, the ESP32 in an Agon Light board, which is a very highly customized, very, very low cost chip that can do a lot. But here I want the logic to be explicit. I want Boolean logic to be visible to the user and allow the user to play with it, because it's an educational platform. It's not a gaming platform. This is educational. This allows you to see how a computer system, which can support many CPUs, is put together all the way down to the individual gate level, to the individual propagation delay. This is what this gives you. So there is a price for this, which is the three CPLDs and the 2 dual ported memories to allow the video circuit to be asynchronous with the computer proper, which also has educational advantages. Now, to give you an idea of the design itself, it basically has 2 signal layers. I will hide the copper areas so we can see better, and I will hide the silk screen so we can see better. So here on top in red, that's the top signal layer, and in blue at the bottom, that's the other signal layer. So there are only 2 signal layers and 2 planes in between for ground and VCC, but the signals are routed in blue and red lines, as you can see in here. There isn't really a preferential direction like we do in through-hole boards. Like the top layer is horizontal and the bottom layer is vertical. That facilitates the routing a lot. Here it's SMD. It's not through hole, so we need to put vias to route every signal. So preferential directions are not the way to go here. You have to use your mind a little more. It's a little more difficult to route the design, because we don't want to go via hopping. We don't want one network to have 5 hops from one layer to the other via vias, because that introduces a lot of impedance mismatches, introduces reflections, compromises signal integrity. So the idea here is to minimize the number of times you hop, and to avoid branching. You don't want any net to look like a crab. You want it to look like a snake. It goes from A to B, from B to C, from C to D, as opposed to from A to B, A to C, and A to D. You don't want that, because that creates, each branch will have a different resonant frequency. So each branch will cause reflections at a different frequency, and those reflections will add up because they are in the same network. Oh no, you don't want that. So these are the 2 things you have to keep in mind. Minimize via hopping, minimize branching, and minimize length. And do it in such a way that you can route everything in 2 layers. This is a very complex design as far as routing, because it has 220 different nets. That's quite a lot for a small system. And that's part of the reason I don't want to force the commercial party to have to redesign this in order to make the trade-offs they prefer, because it's laborious. So I want to do it the way that they prefer, so they can use it straight out of my hands. Just take the Gerber files and make the board. Don't have to redesign anything. Let me show you the buses. The buses are connected to these 3 through-hole resistor banks in here. So we can look at the nets. Look, as you can see here, this line goes there to this pad, and then it goes back out, back in the same direction it came, and goes down. Why didn't I connect it right here between these 2 points? Well, because that would lead to a branch. And I don't want a branch. I don't want a crab. I want a snake. I want it to go from here to there, and from there to here, and not to have a branch here. That's the reason. Sometimes branches are unavoidable. Let's see, this one. Yeah, this one has 1 branch. If you look here, this is a small branch. It goes from this to the pad below, to the here to the pad below. But it's a very small branch, so it will only reflect or resonate with very, very high frequencies. And this board is running at maximum. The pixel clock is 25.175 megahertz, so that's not high. Even if you take the harmonics into consideration, you're still at around 250 megahertz for the highest harmonics, which is still okay. This line is so short that we would be talking at the gigahertz level for something to resonate and reflect on this branch here. So that's okay. There are some larger branches. Let me look for it, because I remember there was a net. Oh, it's this net here has a larger branch. No, it doesn't. You see, there's a little branch here to go to the buffer over here, but it's very small. And there is a branch. Where is it? Here to go up, also very small. No, it's okay. So I did manage to remove all the significant branches. The branches that are left are very small, very short, and each of these networks is basically a snake. So that's good. It's good for signal integrity. You also notice that for every signal via, I have a ground via right next to it. So this is a signal via for address line 1. There's a ground via right next to it. The same for address line 2, ground via right next to it. The same for everything. This is a clock. I have 2 ground vias next to it. And this is to provide a return path for the current. Remember, every electrical circuit is a closed loop. You know, when you connect a battery to a toy, it's a closed loop. It goes from the positive to the toy and from the toy back to the negative. So the current has to flow in a loop. Otherwise, you don't have power. The same goes for every signal, every logic signal. It's a little transmission line. So wherever the charge goes, charge comes back as well. So when you put charge on a line going to the clock pin of in this case, this is the 6502. That's the 6502 clock. When charges go there on the positive transition of the clock, charges have to go back. And if you don't put a ground via, which we call a return path via, next to a logic via, the fields will be such that they will find a return path, but they may find a return path here. And in the process of doing so, it may interfere with something else, compromising signal integrity. So if we provide a return path right next to a signal via, then the return current will not spread. The fields will not spread. The field fringes will connect sideways here between these two. They will be very tight, very compact. They will not interfere with anything else. That's why there are these return path vias everywhere. Now, this is good practice for high-speed boards. This is not a high-speed board. Why am I doing this? Because it's a very dense board as far as routing is concerned. So even though there aren't many high frequencies here, the highest harmonics will still be just below 250 megahertz. There is a lot going on. So it's good to keep the field fringes when the signal goes vertically down a via. The field fringes will be around the signal like this, and you don't want them to spread far away. You want to put a via right next, so they couple between the signal via and the return path via locally between these two, as opposed to going from one of them far away to the other. They couple like this. That's the idea. It's to improve signal integrity. That's all I wanted to talk about today. Let me make everything visible again. So this is what CERBERUS 2100 will probably look like. It's not going to happen soon because we have to wait for the parts to become available end of May even. So we'll have a prototype by early June, and if it all works, it may become available on GitHub for you later in the summer. It will work because CERBERUS 2080 works, and we have a load of firmware for it. We have basic interpreters for both 6502 and the Z80 already. We have fourth interpreters for both the CPUs already. We have games, we have assemblers, we have a bunch of things for both CPUs. So we know the overall system works. I'm making some additions here, like I will allow the clock to go from the maximum down to 1 megahertz. In the case the user puts something on the expansion port that is very slow, I'm allowing for CAT to reduce the clock down to 1 megahertz. So that requires one more signal from CAT, one more flip-flop in spacer. Small things that still need to be tested. There are a few other examples. I still have to test them, but I don't see any reason why they shouldn't work. I don't expect to be resource constrained even in Spacer. Spacer uses almost all the logic, but the additions I want to make in order to allow for the bus expansion, for instance, to do a memory read, a memory write. Spacer needs to interpret more signals, process more signals in its logic, but I don't expect that I will run against the limit, even though I'm close to it. I don't expect I will run against the limit. So if I do, then I have a real problem. Because the point of Cerberus 2100 is to allow anything on the bus to be a DMA device, to do direct memory access, to be the master of the system. And for that, I need Spacer to be able to interpret extra signals, a few extra signals. So I hope I can do that. That's the only big question remaining. If that's possible, and I can do that anytime, I don't need to wait for May. I can have a simulation, a simulator and a fitter for this CPLD. I will do it over the next couple of weeks. That working, I don't expect any problem. So if the chips become available as predicted, then at some point in the summer, there will be a GitHub repository with all the information. And maybe there will be a commercial party manufacturing this in volume, selling this in volume, hopefully for a very good price, given what the system can do as an educational platform. Not a gaming platform. This is an educational platform that shows you all the way down to the gate level how a computer is put together and allows you to make your own variations by reprogramming the CC3 CPLDs and the firmware of the microcontroller here, which is the I/O controller, in C using freely available compilers like the Arduino IDE. So that's the point. So you should regard the price under that light. We make choices to use quite expensive chips here in order to make your life easier when you're studying this or playing with it as a designer, not playing with it as a gamer. That's the idea. Hopefully universities will like it too, and the price point will be such that they will be able to afford quite a few of these units for their students. All right, that's it from me this time. I will get back to Talos now, which I have been neglecting because I'm at a point now where things are more or less trivial, and it turns me off, but I have to finish that. So that's probably the subject of my next video. Till then, take care. I'll see you next time.